Late winter, 1897, Alaska gold camp, where 40-mile-per-hour winds sweep unchecked across frozen tundra. While fellow prospectors raced to pitch standard canvas tents before the killing cold arrived, Canadian miner Thomas McCarty was cutting massive blocks from wind-packed snow, methodically stacking them into curved walls around his campsite. His neighbors called it wasteful, called it Eskimo fording. Why waste precious mining time building snow walls when a simple tent and wood stove had worked for every frontier camp? Then came the 7-day blizzard, sustained winds 65 miles per hour, temperatures 30 below zero. Standard tents collapsed. One man died from exposure. Surviving camps burned 8 cords of wood in 4 days, yet interior temperatures still dropped to 10 below. But McCarty's tent, sheltered behind those wasteful snow brick walls, maintained 15 degrees above zero while burning less than half the fuel. What did this Canadian prospector understand about surviving Arctic winds that generations of proven frontier wisdom had completely missed? Thomas McCarty had arrived in the exposed Gold Camp region of Alaska's interior 3 weeks before that first killing wind hit. The Canadian prospector carried more than standard mining gear in his pack. He brought memories of Yukon winters spent among indigenous hunters who had shown him how wind could kill a man faster than cold alone. Where other miners saw empty tundra suitable for quick camp setup, McCarty studied the landscape with different eyes, noting how the river flats offered no natural windbreaks and how the prevailing northwesterlies swept unchecked across miles of frozen ground. The standard method seemed reasonable enough at first glance. Prospectors throughout the region followed the same proven formula: erect canvas tents or rough-hewn wood shanties, maybe throw up a few driftwood logs for partial wind screening, then rely on small wood-burning stoves to maintain livable temperatures inside. The approach had worked in California mining camps, in Colorado high country, even in the Canadian Rockies. Speed was everything in gold country. The sooner a man got his shelter up, the sooner he could start working his claim and pulling color from the frozen ground. But Alaska's interior tundra presented conditions that broke those established rules within days. When the first sustained winds arrived, 40 to 50 mile-per-hour gusts that turned the camp into a freezing hurricane, the standard shelters revealed their fatal limitations. Canvas walls whipped and snapped like ship sails in a gale. Guy ropes stretched beyond their breaking point. One tent collapsed completely, trapping its occupant under heavy canvas and threatening suffocation. Another miner's stove began backdrafting when the wind created negative pressure inside his shack, filling the small space with choking smoke and forcing him to extinguish his only heat source. The fuel consumption became catastrophic. Where miners had calculated 1 cord of wood per week for heating, they found themselves burning 3 cords in the same period just to maintain temperatures above freezing. The wind sucked heat from their shelters faster than the small stoves could produce it. Men who had brought carefully rationed wood supplies watched their winter fuel disappear in days. 2 prospectors suffered exposure injuries when their inadequate heating failed during a particularly brutal night, resulting in frostbitten fingers that would plague them for months. McCarty observed these failures while methodically studying the materials at hand. The wind-packed snow around the camp had compressed into dense blocks under weeks of constant pressure. When he cut into it with his prospector's saw, the snow held its shape like masonry stone. This was not the loose powder snow of gentler climates. This was building material shaped by the very forces that were destroying his neighbors' shelters. His background gave him context that others lacked. During previous winters in the Yukon Territory, he had watched Inuit hunters construct wind-resistant shelters from similar snow blocks. The technique was not mysterious. It was practical engineering adapted to available materials. The hunters would saw blocks roughly 1 foot thick and 2 feet long, then stack them in interlocking patterns that created walls capable of deflecting even savage winds. The principle was simple. Instead of fighting the wind with heat alone, first stop the wind, then let a smaller heat source do its work in the protected space. The immigrant masons McCarty had worked alongside in earlier mining ventures had taught him complementary lessons about wind load resistance. Scandinavian builders knew that curved walls deflected wind more effectively than flat surfaces, and that proper foundation work prevented structures from shifting under lateral pressure. These old world techniques, developed in northern European winters, offered proven solutions for the same environmental challenges he now faced. When McCarty began cutting blocks from the compacted snow around his tent site, his fellow prospectors reacted with predictable scorn. They called his methodical block sawing Eskimo fording, a waste of precious daylight that should be spent on more profitable activities. Camp managers insisted that time spent building elaborate shelters was time stolen from mining operations. The established hierarchy of frontier survival placed speed above all other considerations. Real miners, according to camp wisdom, pitched their tents fast and got to work. But McCarty had calculated the economics differently. He understood that a miner who burned 3 cords of wood per week trying to heat an inadequately sheltered tent would spend more time hauling fuel than extracting gold. A prospector who suffered frostbite injuries would lose weeks of productive work. Most critically, a man whose shelter failed completely might lose everything, including his life. McCarty's initial construction was modest but purposeful. He sawed blocks of the compacted snow approximately 12 inches thick and 18 inches long, creating building units he could handle alone. Working in the early morning hours before the day's mining began, he stacked these blocks 3 to 4 feet high along 3 sides of his tent, leaving the entrance side partially open for access. The wall curved slightly, following the mason's principles he had learned, to deflect rather than simply block the prevailing winds. The other prospectors watched his daily progress with growing skepticism. Why dig foundation trenches for snow blocks when a simple tent setup took half an hour? Why spend days building walls when proven frontier methods required only basic equipment and established techniques? The assumption underlying their criticism was that generations of mining camp experience had already identified the optimal survival strategies. If elaborate wind walls were necessary, surely previous miners would have built them. This assumption would prove devastatingly wrong. The environmental conditions of Alaska's exposed interior exceeded the parameters that had shaped mining camp traditions in more temperate regions. Standard methods that worked adequately in California or Colorado failed catastrophically when applied to sustained sub-zero temperatures combined with unrelenting wind. McCarty's quiet rebellion against established practice was not philosophical. It was practical adaptation to conditions that demanded different solutions. His snow block walls would soon face their ultimate test, but first they had to survive the daily mockery of men who measured wisdom by speed and tradition rather than environmental effectiveness. The critical flaw in standard camp layout became apparent to McCarty during the first week of sustained winds. Most prospectors had oriented their tents with entrances facing toward the prevailing northwesterly gusts, following the mistaken logic that direct airflow would help ventilate smoke and moisture. Others had positioned their shelters randomly across the flat tundra, treating site selection as irrelevant since no natural windbreaks existed anyway. This approach ignored fundamental principles that indigenous Arctic builders had understood for generations: that wind direction, shelter orientation, and the creation of protected microclimates were inseparable elements of survival engineering. McCarty's enhanced wall system grew from careful observation of how wind behaved across the camp's terrain. The northwesterly gusts swept across the river flats in predictable patterns, accelerating as they encountered obstacles and creating zones of turbulence that could be either devastating or beneficial depending on shelter placement. Rather than simply blocking wind with a straight barrier, McCarty designed his snow brick walls to redirect airflow around a protected courtyard space. His wall configuration extended 10 to 12 feet laterally from his tent on 3 sides, creating a horseshoe-shaped enclosure that channeled wind over and around the shelter rather than through it. The engineering principle behind his curved wall design came directly from Scandinavian masonry techniques adapted for Arctic conditions. Immigrant builders from northern Norway and Sweden had long understood that curved stone walls distributed wind loads more effectively than flat surfaces, which concentrated pressure at single points and often failed catastrophically. When applied to snow block construction, This curvature allowed McCarty's walls to deflect rather than merely resist the tremendous lateral forces generated by 60-mile-per-hour gusts. The wall height proved crucial to the system's effectiveness. McCarty discovered through trial and error that walls lower than 4 feet failed to create adequate wind shadow, while walls higher than 6 feet required excessive construction time and materials. His final design settled on 5-foot walls that rose just above the tent's roofline, creating a zone of relative calm in the immediate shelter area, while allowing some air circulation to prevent dangerous carbon monoxide buildup from his wood stove. Within this protected courtyard, McCarty carefully positioned his tent opening away from the prevailing winds, facing southeast toward the natural lee side of his wind wall system. This orientation ensured that his stove exhaust could vent safely without being blown back into the shelter, while the entrance remained accessible even during the worst weather. The positioning also took advantage of whatever limited solar warming was available during the short winter days, as the southeast-facing opening could capture early morning sunlight when it appeared above the horizon. The construction technique itself required precise block-cutting methods that McCarty had learned from an Inuit hunter during his earlier Yukon experiences. The snow blocks had to be cut from wind-compacted snow using a specific sawing motion that preserved the structural integrity of each unit. Blocks cut from loose or recently fallen snow lacked the necessary density and would crumble under their own weight. The compacted snow, however, had been compressed by weeks of constant wind pressure into a material with structural properties similar to soft sandstone. Each block measured approximately 12 inches thick, 18 inches wide, and 24 inches long, dimensions that provided optimal weight-to-strength ratios for single-person construction while maintaining structural stability. McCarty laid the blocks in overlapping courses, similar to brick masonry, with each block spanning the joints of the blocks below it. This interlocking pattern distributed loads evenly throughout the wall and prevented catastrophic failure if individual blocks cracked or shifted. The most innovative aspect of McCarty's system was his use of natural snowdrift accumulation to strengthen his constructed walls. Rather than fighting the wind-blown snow that constantly threatened to bury the camp, he positioned his walls to encourage controlled drifting on the exterior side. This accumulated snow formed a natural buttress that reinforced the constructed wall while providing additional insulation. The technique required careful calculation of wind patterns and drift angles, but when executed properly, it allowed the environment itself to strengthen his defensive structures. The first major test of McCarty's enhanced system came during a 5-day storm in early February of 1898. Sustained winds reached 60 miles per hour with gusts exceeding 70, while ambient temperatures dropped to 18 degrees below zero. The wind chill factor pushed effective temperatures well below minus 40 degrees Fahrenheit, conditions that would kill an exposed human in minutes. Standard tents throughout the camp suffered immediate and devastating failures. Guy ropes snapped under the tremendous lateral loads. Canvas walls tore free from their anchoring points. 3 tents collapsed completely, forcing their occupants to seek emergency shelter with neighbors whose structures were themselves barely surviving the assault. The miners who maintained their shelters faced fuel consumption rates that consumed 6 full cords of wood during the 5-day period, wood that many had not stockpiled in sufficient quantities. Inside McCarty's protected courtyard, wind speeds dropped from 60 miles per hour to less than 10 miles per hour. His tent suffered no structural damage, required no emergency repairs, and maintained internal temperatures between 10 and 20 degrees above zero throughout the storm. Most remarkably, his fuel consumption during the same 5-day period totaled only 2 cords of wood, less than half the amount burned by surviving standard shelters. The temperature differential was equally dramatic, while standard tents that remained standing recorded internal temperatures as low as 15 degrees below zero. Despite continuous heating, McCarty's shelter never dropped below 5 degrees above zero. The protected microclimate created by his wall system had effectively raised the ambient temperature in his immediate area by 25 to 30 degrees compared to exposed conditions. When the storm finally subsided, the contrast between McCarty's intact, comfortable camp and the devastation surrounding it was impossible to ignore. His systematic approach to wind management had not merely survived the test, It had thrived while established methods failed catastrophically around him. Even within his wind-protected courtyard, McCarty recognized that his shelter system remained vulnerable to a more insidious enemy than gusting wind. Heat loss through conduction, radiation, and convection continued to drain warmth from his tent faster than his wood stove could replace it. Standard canvas provided minimal insulation against the radiative cold of the Arctic night, while the frozen ground beneath his tent acted as a massive heat sink that continuously drew warmth downward through the tent floor. The challenge was not simply stopping wind anymore, it was creating a complete thermal envelope that could retain heat efficiently in conditions where the ambient environment worked constantly to steal every calorie of generated warmth. The solution began with McCarty's recognition that his existing wind wall could serve a dual function. Rather than treating the snow brick barrier as merely a wind deflector, he began constructing a second inner wall of more precisely cut blocks, creating a 6-inch air gap between his outer windbreak and this new thermal barrier. This double wall configuration transformed his simple wind protection into a sophisticated insulation system that trapped a layer of still air, one of nature's most effective insulators, in the space between the two snow brick walls. The inner wall required different construction techniques than the outer windbreak. Where the outer wall prioritized structural strength to resist wind loads, the inner thermal wall demanded precision fitting to minimize air gaps between blocks. McCarty developed a technique for cutting blocks with slightly angled faces that interlocked more tightly, creating joints that prevented warm air from escaping through the wall. Each block was trimmed with his prospector's knife to achieve surfaces that fit together with minimal gaps, a process that increased construction time but dramatically improved thermal performance. The air gap between the walls created what Arctic builders called a dead air space, a zone where air could not circulate and therefore could not carry heat away through convection. The 6-inch spacing proved optimal through experimentation. Narrower gaps failed to provide adequate insulation, while wider spaces allowed air circulation that reduced thermal efficiency. The trapped air quickly warmed to temperatures much higher than the exterior ambient conditions, creating an insulating buffer that dramatically reduced heat transfer through the wall system. Ground-level heat loss presented an equally critical challenge that standard tent camping ignored entirely. The frozen tundra beneath McCarty's tent maintained temperatures near 0 degrees Fahrenheit, even when his stove heated the interior air to 20 degrees above zero. This temperature differential created a constant conductive heat drain that forced his stove to work continuously just to maintain basic comfort levels. The canvas tent floor provided no meaningful barrier against this heat sink effect. McCarty's solution drew from Scandinavian log cabin construction techniques adapted for temporary structures. He constructed a raised platform using available driftwood and spruce logs, elevating his tent floor 8 inches above the frozen ground surface. The platform framework consisted of parallel logs spaced 18 inches apart, supporting a decking of smaller branches and driftwood planks that created a stable floor system. This elevation broke the direct conductive connection between his living space and the frozen ground, immediately reducing heat loss through the floor. The space beneath the raised platform was filled with insulating materials that transformed it from a simple elevation system into an effective thermal barrier. McCarty layered spruce boughs, available animal hides, and even discarded canvas scraps into the 8-inch cavity, creating a multi-layer insulation system that trapped air while providing additional thermal mass. The spruce boughs were particularly effective because their needle structure created countless tiny air pockets that resisted heat transfer while remaining relatively dry even in the humid environment beneath the tent. Inside the tent itself, McCarty implemented a double wall system using available materials to create an interior thermal envelope. He hung spare blankets and canvas pieces from the tent's internal framework, creating an air gap between the outer tent wall and this inner liner. This configuration worked on the same principle as his double snow brick walls, trapping a layer of still air that provided insulation while reducing condensation problems that plagued standard single-wall tents. The interior liner system required careful attention to ventilation management. Complete sealing would have created dangerous carbon monoxide buildup from his wood stove, while excessive ventilation would negate the thermal benefits. McCarty developed a technique of sealing the liner at floor level using snow blocks pressed against the tent's perimeter, while maintaining small ventilation openings near the roof peak that allowed just enough air circulation to prevent dangerous gas accumulation. The combined effect of these thermal envelope improvements became apparent during the extended cold spell that followed the major windstorm. Night temperatures dropped to 30 degrees below zero, conditions that had previously forced continuous stove operation just to prevent interior freezing. With his enhanced thermal system in place, McCarty's tent maintained interior temperatures near 20 degrees above zero throughout the night, while his stove operated at reduced output. The fuel economy improvements were remarkable. Where his previous heating system had required constant feeding of the wood stove every 2 to 3 hours throughout the night, the improved thermal envelope allowed him to load the stove before sleeping and maintain comfortable temperatures until morning. His nightly wood consumption dropped from approximately 1/8 of a cord to less than 1/12 of a cord, a 25% reduction in fuel use during the coldest part of each 24-hour cycle. Frost and condensation problems that had plagued his earlier tent setup virtually disappeared with the double wall configuration. The inner liner maintained surface temperatures warm enough to prevent water vapor from condensing and freezing on the tent walls, a critical improvement that eliminated the daily chore of scraping ice from the interior surfaces and prevented the gradual accumulation of ice that had reduced interior space in standard tents. The thermal mass effect of his snow brick walls provided an unexpected additional benefit. The large volume of snow in his wall system absorbed heat during the day when solar radiation and stove operation warmed the protected courtyard, then slowly released this stored heat during the night hours when temperatures dropped. This thermal flywheel effect moderated temperature swings and reduced the peak heating loads his stove needed to handle during the coldest pre-dawn hours. Testing the complete system during a 3-day period when ambient temperatures never rose above 20 degrees below zero, McCarty's enhanced thermal envelope maintained interior temperatures between 15 and 25 degrees above zero while consuming less than 2 cords of wood. Neighboring standard shelters that survived the same period burned over 3 cords while struggling to maintain interior temperatures above 5 degrees above zero. With his wind protection and thermal envelope systems operational, McCarty turned his attention to optimizing the heat source itself. Standard mining camp practice treated wood stoves as simple fireboxes. Load them with whatever fuel was available, burn hot when cold, bank the fires when sleeping. This crude approach ignored fundamental principles of combustion efficiency and heat distribution that could dramatically improve fuel economy. McCarty had observed a critical flaw in how most miners positioned their stoves, placed randomly within tents with no consideration for how radiant heat could be captured and utilized by surrounding structures. McCarty's stove placement strategy treated his heating system as an integrated component of his entire shelter design, rather than an isolated appliance. He positioned his cast iron camp stove on his raised platform system, but critically, he located it near the inner thermal wall rather than in the tent's center. This positioning allowed the stove's radiant heat to warm the snow brick wall directly, which then acted as a thermal battery that continued radiating stored heat long after the fire burned down. The 6-inch air gap in his double wall system became a convective heat distribution channel that carried warm air upward along the wall surface, creating a natural circulation pattern that heated the entire protected courtyard space. The stove's chimney routing required precise engineering to work effectively within his courtyard system. Rather than venting straight up through the tent roof as standard practice dictated, McCarty extended the stovepipe horizontally for 18 inches before turning upward, creating what experienced woodsmen called a heat reclaim bend. This horizontal section extracted additional heat from the exhaust gases before they escaped into the atmosphere, while the extended routing kept the hot pipe within the thermal envelope, where its radiant heat contributed to interior warming rather than being lost outside. Wood preparation became a sophisticated process that separated McCarty's operation from the inefficient fuel practices of neighboring camps. Standard practice involved burning whatever wood was available in whatever condition miners found it, often partially green timber with high moisture content that produced more smoke than heat, while requiring constant attention to maintain adequate combustion. McCarty constructed a specialized wood-drying shelter using snow blocks arranged as a lean-to structure against his outer windbreak wall, creating a protected space where cut wood could season properly even in sub-zero conditions. The wood-drying technique leveraged the thermal differential between his protected courtyard and the exterior environment. Wood stored in this lean-to shelter experienced temperatures 15 to 20 degrees warmer than ambient conditions, while remaining protected from additional moisture from snow or sleet. McCarty cut all his fuel wood to uniform 12-inch lengths that fit his stove firebox optimally, then split the pieces to consistent thickness that promoted even burning and efficient heat release. This standardization allowed him to calculate fuel loads precisely and maintain consistent heat output throughout planned burning cycles. The pre-drying process reduced wood moisture content from 30 to 40%, found in fresh-cut timber, down to 15 to 20% after several days of protected storage. This moisture reduction had dramatic effects on combustion efficiency. Dry wood ignited more readily, burned at higher temperatures, produced minimal smoke and creosote buildup, and delivered approximately 30% more usable heat per pound than the green wood his neighbors continued burning. The time invested in proper wood preparation returned immediate dividends in reduced fuel consumption and improved heating performance. McCarty developed a thermal cycling technique that maximized the heat storage capacity of his snow brick wall system while minimizing active fuel consumption. Each evening before entering his tent, he loaded his stove with dry wood and burned a full charge for 30 to 40 minutes, directing maximum heat output toward his thermal wall during this preheating period. The snow brick walls absorbed this concentrated heat input, raising their internal temperature well above ambient conditions and storing thermal energy in the mass of the wall system. After this preheating cycle, McCarty reduced his stove output to a maintenance level that provided just enough heat to replace ongoing losses through ventilation and remaining conductive pathways. The heated walls continued radiating stored energy throughout the night, maintaining comfortable interior temperatures while the stove operated at minimal output. This technique required careful timing and fuel management, but it reduced overnight wood consumption by approximately 40% compared to standard practice of maintaining constant high heat output. The most innovative element of McCarty's heating system was his adaptation of hot water heat storage techniques learned from an Austrian immigrant who had built alpine huts in the European mountains. McCarty began heating water in a cast iron pot during his evening preheating cycle, then transferring the near boiling water to a sealed metal container that he placed on his sleeping platform. This improvised hot water bottle provided localized radiant heating that kept his immediate sleeping area warm for 6 to 8 hours without requiring any additional fuel consumption. The hot water technique proved particularly valuable during extreme cold snaps, when even his optimized heating system struggled to maintain adequate comfort levels. The heated water container could raise temperatures in his immediate sleeping area by 10 to 15 degrees above the general interior temperature, providing a warm microenvironment that ensured comfortable rest, even when fuel conservation required reducing overall heat output. The thermal mass of the heated water released its stored energy gradually throughout the night, creating a sustained warming effect that lasted well into the following morning. Testing his complete fuel management system during a week-long period when temperatures never rose above 10 degrees below zero, McCarty achieved remarkable efficiency improvements. His daily wood consumption averaged 3/4 of a cord compared to the 2 full cords burned by neighboring camps that maintained barely adequate interior temperatures. His preheating and thermal cycling techniques allowed him to maintain interior temperatures between 20 and 30 degrees above zero, while his neighbors struggled to achieve 15 degrees above zero despite burning nearly 3 times as much fuel. The combustion efficiency improvements eliminated many of the maintenance problems that plagued standard camp stoves. McCarty's dry, properly sized fuel burned cleanly with minimal creosote formation, reducing chimney cleaning requirements and preventing dangerous backdrafting incidents that had forced neighboring miners to extinguish their stoves during windy periods. His systematic approach to fuel management had transformed heating from a constant struggle against the environment into a controlled process that provided reliable comfort while conserving precious wood resources for the long winter months ahead. The ultimate test of McCarty's integrated survival system arrived in early spring of 1898 when a massive low-pressure system stalled over the Gold Camp region. Weather patterns that normally brought brief, intense storms instead locked into a sustained assault that would persist for 7 consecutive days. Barometric pressure dropped to levels that made accurate measurement impossible with the camp's crude instruments, while wind speeds built steadily from the 40-mile-per-hour gusts that had already proven devastating to 65-mile-per-hour sustained velocities, with peak gusts approaching 80 miles per hour. The temperature profile of this storm differed critically from previous weather events. Rather than brief cold snaps followed by warming periods, temperatures dropped to 30 degrees below zero on the second day and remained at or below that level for 5 continuous days. The combination of sustained extreme wind with prolonged extreme cold created conditions that exceeded the survival parameters of every established mining camp technique. Standard shelters that had managed to survive previous storms faced a test that pushed them far beyond their design limits. Supply lines into the camp became completely severed when the storm's intensity made travel impossible even for experienced dog sled teams. Wood hauling operations ceased entirely after the first day when visibility dropped to less than 10 feet, and wind speeds made it lethal to venture outside established shelter areas. Miners who had not stockpiled adequate fuel supplies found themselves trapped with dwindling resources and no possibility of resupply until weather conditions improved. The failure cascade among standard method camps began on the third day when accumulated wind loading finally exceeded the structural capacity of guy rope and stake systems that had been stressed continuously for 72 hours. The first tent collapse occurred during the pre-dawn hours when a critical guy rope snapped under sustained tension, causing the entire structure to fold inward and trapping 2 men beneath heavy, ice-laden canvas. Rescue efforts in 65-mile-per-hour winds required 4 men working in relay teams to extract the trapped miners, both of whom suffered exposure injuries during the evacuation process. The catastrophic failure of the Jenkins brothers per camp illustrated the deadly mathematics of inadequate fuel preparation. Their standard tent and stove setup had consumed 6 cords of wood during the first 4 days of the storm, while maintaining interior temperatures that never rose above 5 degrees below zero. When their wood supply ran out on the 5th day, interior temperatures plummeted to 25 degrees below zero within 6 hours. The brothers were forced to burn personal belongings, including clothing, wooden tools, and even parts of their mining equipment in a desperate attempt to maintain survivable temperatures until rescue became possible. Thomas McCarty's systematic approach to fuel stockpiling had anticipated exactly this scenario. His wood-drying lean-to contained 12 cords of properly seasoned timber, cut to optimal lengths, enough fuel for 3 weeks of normal heating or 1 week of maximum output during extreme conditions. The pre-drying process that his neighbors had mocked as wasted effort now provided the combustion efficiency that kept his heating system operational when green wood would have failed to generate adequate heat. The snow-loading characteristics of McCarty's double-wall system revealed an additional engineering advantage that had not been apparent during shorter storms. As wind-blown snow accumulated against his outer windbreak wall, it formed a natural insulation layer that actually improved the thermal performance of his shelter system. The accumulated snow created what engineers would later term beneficial loading, additional mass that enhanced rather than threatened structural integrity while providing extra insulation that reduced heat loss through the walls. McCarty's courtyard design proved critical during the most dangerous phase of the storm when horizontal snow created whiteout conditions that made navigation impossible beyond a few feet. His protected interior space remained relatively clear of drifting snow, allowing him to access his wood supply, maintain his stove, and monitor his shelter systems even when exterior visibility approached zero. Miners in standard camps found themselves unable to reach wood piles located just yards from their tents, effectively cutting them off from their fuel supplies during the storm's most critical hours. The thermal mass effect of McCarty's snow brick walls provided unexpected benefits during the extended cold period. The large volume of snow in his wall system had absorbed and stored heat during the warmer pre-storm days, creating a thermal reservoir that continued releasing stored energy throughout the cold snap. This thermal flywheel effect moderated temperature swings inside his shelter, preventing the rapid temperature drops that plagued standard tents when stoves burned low or required refueling. Temperature measurements taken during the storm's peak revealed the dramatic performance differential between McCarty's system and standard methods. While neighboring tents that remained standing recorded interior temperatures as low as 15 degrees below zero. Despite continuous maximum heating, McCarty's shelter never dropped below 5 degrees above zero and typically maintained temperatures between 10 and 15 degrees above zero during the coldest periods. His fuel consumption during the entire 7-day storm totaled 3 cords compared to the 8 to 12 cords burned by standard camps that survived the event. The structural integrity of McCarty's system remained uncompromised throughout the storm, while standard shelters suffered progressive damage that accumulated over the 7-day period. His curved wall design continued deflecting wind effectively, even as sustained 70-mile-per-hour gusts created conditions that destroyed conventional windbreaks built by other miners. The interlocking snow block construction distributed loads evenly throughout the structure, preventing the catastrophic failure points that brought down simpler wind barrier systems. When the storm finally subsided on the 8th day, the contrast between McCarty's intact, fully operational camp and the devastation surrounding it was impossible to ignore. 4 tents had collapsed completely, requiring their occupants to crowd into remaining shelters under conditions that barely provided survival-level protection. 2 miners had suffered serious frostbite injuries that would require medical evacuation when travel became possible. 1 man had died from exposure when his inadequate shelter failed during the storm's most severe phase. The quiet vindication began immediately. Camp manager Dutch Henderson, who had previously dismissed McCarty's building efforts as time wasted from mining operations, approached the Canadian Prospector on the morning after the storm with notebook in hand. Henderson spent 2 hours examining the snow brick wall construction, asking detailed questions about block cutting techniques, wall spacing requirements, and thermal management principles. His notes would become the basis for new shelter construction guidelines distributed to incoming miners later that season. Fellow prospector Mike Torino, whose standard tent had barely survived the storm despite burning over 10 cords of wood, began cutting snow blocks the following week. Within a month, Torino had constructed his own curved windbreak system using techniques learned directly from McCarty's example. The fuel savings during subsequent smaller storms convinced 2 additional miners to adopt similar methods before the end of the winter season. By late spring of 1898, virtually every exposed winter camp in the region had implemented some version of snow brick wind protection. Mining supply companies began including snow cutting tools in their standard equipment lists, while regional newspapers published articles describing proper techniques for Arctic shelter construction. McCarty's integration of indigenous building methods with immigrant craftsmanship had transformed from individual survival innovation into accepted frontier practice, proving that environmental adaptation rather than environmental resistance provided the key to survival in Alaska's unforgiving interior.